In this video, we are going to be looking at how to convert a quadratic such as this into standard form. And I'm getting this problem from the handout Writing and Graphing Quadratics. This is page 12, problem number 31. So we're told to write this quadratic in standard form. The first thing that we need to realize is that this is not in standard form, and we need to know what standard form looks like. So when I'm looking here, I can see that this looks like y equals ax minus h squared plus k. So because it has that form, I know that this here is in vertex form. So this is vertex form. So given the vertex form, I should be able to locate the vertex. So I know that the vertex is my h and my k. So my vertex is 2, -4. And I also know that I have a stretch of 3 right here. So I stretched 3, which means it got skinny. So I always like to give like an idea of what it is that I'm looking at, and I'll show you later how we're going to use the Desmos calculator. So I know that this is positive, which means that my quadratic opens up, and I also know that it's skinny. So I'm just going to draw a sketch. So it's going to look something like this, and my vertex is at 2, -4. Okay, that's just review. That's just to show you that I can get my vertex and a general idea of what this function looks like without even having to put it in the calculator. But that's not what this is asking. This is asking for us to write it in standard form. So let's do a little bit more review here before we go on. So I know that vertex form looks like y equals ax minus h squared plus k. But standard form, also known as general form, and I'm going to put this in parentheses and put general form, looks like y equals ax squared plus bx plus c. So these two look totally different. This one here gives me my vertex. So my vertex is at hk, but this one doesn't give me that. Okay, it's just general, it's pretty, and we could also look at it as it is simplified. So this here is a simplified form of our quadratic. Okay, so how are we going to get it into standard form? So we have to do math. So we're going to have to do the order of operations. So you must do order of operations. Okay, so we all know this as GEMDAS, where G is grouping, E is exponents, M and D is multiplication or division going from left to right, whichever comes first, and A and S is addition, subtraction going left to right, whatever comes first. Okay, so let's look at our original problem. Y equals 3, x minus 2 squared minus 4. So the first thing I notice is that I have a grouping, okay? So this right here is my group. That's all my group. So I look inside my group, and there's nothing that I can do inside that group. So that means I got to just leave it like that. Which means that the next thing that I have to look at is exponents. And I do have an exponent. I have an exponent right here. And that exponent is doing something to that entire number. Okay, so what we're going to do now is we're going to take a little commercial break, and I'm going to talk to you about exponents. So if you're writing this in your notebook, you can write it on the page to the left. So let's talk about exponents. So an exponent is something that's squared, cubed, fourth root, to the fourth degree, fifth degree, and so on. Okay, so let's just look at expanding exponents. And what does that mean exactly? Well, first of all, let's look at this thing called perfect squares. So what are perfect squares? How do I get perfect squares? Well, if I take any number, if I take 1 and I square it, that's going to give me a perfect square. So that's the same as 1 times 1. I've just expanded my squaring, which gives me 1. Well, that wasn't very exciting. If I take the number 2 and I square it, that gives me expanded would be 2 times 2, which gives me 4. And if I were to take the number 3 and square it, that gives me 3 times 3, which is 9. I'm going to stop here at 4. If I were to take the number 4 and I were to square it, I'm going to expand that to be 4 times 4, which gives me 16. Okay, so what I want to point out is these numbers right here, and there are more, many more, those there are my perfect squares. Okay, those are my perfect squares. So why do we call them squares? And why are they perfect? So if I have a square and this side here is 1 and this side here is 1, that gives me a perfect square because all my sides are the same. That area is 1 square unit. If I were to look at 4 as a perfect square, what does that mean? That means I have 2 on this side and 2 on this side. So I'm going to segment it like that. So this side is 2 in length, and this side is 2 in length. So that gives me an area of 4. Let's do this with my 3 squared. I'll do it right over here. So 3 squared. So if I go down 1, 2, 3, and I go over 1, 2, 3, so we can see that this side is 3, and this side has also a length of 3, but I have an area of 9. Okay, so let's just look at one more because I'm going to use this as an example for what we're doing in our problem, just because I like the number 4. So the same thing with 4, that would mean I would go down 1, 2, 3, 4. So I have a length of 4 and 1, 2, 3, 4, and a width of 4. So you're going to see that I get 16 square units in there. So this is 4. And this is also 4. So my area is 16. So anytime we square anything, we always get area. Okay? So let's write that down because that's important to remember. Squaring always gives area. Okay, so that means that our quadratic is actually giving us an area because it is squared. But before I get ahead of myself, I want to show you something. So, we know that 4 times 4 is equal to 16. I just proved it to you, right? But we can write 4 in many different ways, right? I could write 4 as, let me just write it over here. I'm going to write 4, I could write 4 as 1 plus 3. That's the same as 4, isn't it? I could write 4 as 2 plus 2, right? That's the same as 4. I could also write 4 as 5 minus 1. Or I could write 4 as 6 minus 2. So I have an infinite number of ways of writing 4. For what I'm going to do today, I'm going to use 6 minus 4 because it's going to parallel what we're going to do. So instead of writing 4 times 4, I'm going to rewrite my 4 to be 6 minus 2 times 6 minus 2. And we know that that equals 16. Same exact problem, just written differently. Okay? So remember how we did this area model here? We're going to do the same area model. Although I'm not going to break it up the same exact way. So what I'm going to do, now yes, it doesn't look like a square, but that's okay. That this length here is 4, but instead of writing 4, I'm going to write 6 minus 2. And this length here is the same, you just have to bear with me, is also going to be 6 minus 2. Notice I wrote the minus 2 in front of the 2. So in this case, I'm only going to split this up into a box of 4 because I have 2 numbers here and I have 2 numbers here. So now I want to find the area of this box. So I'm going to go 6 times 6, that's 36. The area of this box is negative 2 times 6, which is negative 12. The area of this box is 6 times negative 2, which is also negative 12. And the area of this box is negative 2 times negative 2, which is positive 4. So if I add up all my areas, that is going to be the same as 36 minus 12 plus 4. And if you put this in your calculator or you work it out doing mental math, you get 16. So I get the same exact answer. Okay. So we have to use this method, there's another method and I can show you that later, to find the area of something that's squared. Let me show you why this here would not work. So this here, I'm going to show you now, this is wrong to do it like this, and I'm going to show you why. If I have 6 minus 2 squared, and I try to distribute that, remember our order of operations says we have to do what's inside the grouping first. I cannot distribute that because then I would get 36, and then that would either be minus 4 or plus 4. It doesn't really matter. I'll do it either way. Okay, so this one here gives me 32, and this one here gives me 40. Clearly not 16. So I cannot do it that way. I have to set it up as an area model. So what I want to show you is this 6 minus 2 times 6 minus 2, that's expanded. If I were to write it as an exponent, it's 6 minus 2 all squared. In our original problem, we had y equals 3 times x minus 2 squared minus 4. Well, isn't this just like this? This right here looks very much like this, except we don't know what x is. So notice if I write x minus 2 squared, they look almost exactly the same. So if I use this method to multiply this, I'm going to get the correct result. So that's what we're going to do. So back to our original problem. So I have to do my exponents first. So my exponent, I'm going to expand this. I'm going to rewrite this to be y equals, don't skip this step because you're apt to make a mistake, x minus 2 minus 4. Okay, so now I have changed my exponent into multiplication. So now I want to multiply that out. Do not do it under here. Have a workspace off to the side. So remember, this is area. So I have an area of, I guess I'll do it here, x minus 2. And this is x minus 2. So I usually write my binomials first, and then I put in my squares, my boxes. So x times x is x squared. Negative 2 times x is negative 2x. X times negative 2 is negative 2x. And negative 2 times negative 2 is a positive 4. So this is the same as x squared minus 2x minus 2x plus 4. Remember, the box is just a tool. It is not giving me an answer. I cannot leave it like that. Now I have to notice that these here are like terms, so I can simplify this to x squared minus 4x plus 4. So what I want to point out is that this number right here, x squared minus 4x plus 4, is the same exact number as the quantity x minus 2 times x minus 2. So I highlighted that on purpose because I'm going to put that answer there. This is still being grouped because it's being multiplied by a 3, so this is one number. So I'm going to rewrite this as y is equal to 3, parentheses, and then this minus 4. So I'm going to stress this minus 4 is easy to lose it. That's why I'm showing you very systematically. So now I'm going to write an x squared minus 4x plus 4. So now this 3 is only being multiplied to everything inside the parentheses. I'm going to write it down here a little bit, give me a little bit more space. So y is equal to 3 times x squared is 3x squared. 3 times negative 4x is negative 12x. And 3 times 4 is a positive 12. Do not forget this minus 4. That minus 4 has to come down or you're going to get the wrong answer. So I have to remember to bring that along for the ride. Now I can see that these two are like terms. So that gives me y is equal to 3x squared minus 12x plus 8. So this equation, that is my general form. My vertex form, which was my original, which was x minus 2 squared minus 4. This is vertex form. This is general form. These here are the same exact function. So these here are the same function written in two different forms. So I'm going to show you how you can check that using the Desmos calculator to make sure you've done it correctly. So I've gone ahead and I've put in the vertex form of the quadratic that we are trying to write in standard or general form into my Desmos calculator. And you can see we talked about the vertex, and here's a vertex at 2, -4. So let's just go ahead and let's put in what we solved. We solved, or I should say simplified, this vertex form into standard form, and we got 3x squared minus 12x plus 8. No, yes, plus 8. Okay, so you can see that my blue function, that quadratic, graphed exactly on top of the red. So watch, I'm going to turn the blue off. There's my red, and I'm going to turn the blue on. It went exactly on top. There is no difference. They're the same exact equation. One is written in vertex form, and the other is written in standard form. The one thing that I do want to point out is that if I were to make x equal to 0, and everywhere along the y-axis is where x is 0, I can find my y-intercept. So if I were to do that, I'm going to see that I have a y-intercept where x is 0, and my y-intercept is where y is 8. Can't see it up here because it's right here. So the only thing that you can really gather from your standard form is the y-intercept. And I want to stress that the y-intercept is really not very important. It's just helpful to graph something. So don't get hung up on the y-intercept, because we're going to learn later that all of the action happens at our x-intercept, and we'll be learning that later.